Um, so in regards to meeting the client's desires around a sustainable development, something that's going to be thermally comfortable, employ passive principles, is that something that you have covered much in your studies thus far? No? No? Shaking heads? Not really? A little bit? A little bit? So, yeah. All right, well, we'll go through it in reasonable sort of detail then today, because it is, I think it's not that one. I think it's a very important thing for us to, to certainly understand as designers and understand that the interplay between things such as solar access, thermal mass, and cross flow ventilation. It's not how to say it. Often you've got complementary or competing factors that you have to weigh up with a design, and you also got to balance that against other desires of your client, such as views and also orientation on the site in terms of access and things like that. So some of the things in design are non-negotiable. Like topography is fairly non-negotiable. You've got a site, you have to deal with that. How you deal with that, is either going to be practical, impractical, cheap, or expensive. And so some of these things are fairly non-negotiable, but you can weigh up all of those competing or factors that work together to work out your best possible design. And yeah, and starting from passive solar principles and passive design is probably a good point. So within this section, what's the industry standards and instructions? Or we've got information about drawings and drawing process and so on. We'll be going through that later as we start getting more into the drawing section. By all means, have a look here, because we'll be starting to muck around and familiarise ourselves with that Revit model later today. Possibly it was in product information. No, okay, so there's also plenty of design guides and things like that for materials. Much of this not relevant at this point in time for our project one, because it's fairly well given to you. But as we head further into project 2 and project 3, you're going to have to start thinking more about materials, and there's plenty of information there for you. So I've gone into passive design principles of sustainability under industry standards and instruction. So it's that first one there. So click on that and drop it down, and there's a whole host of materials in there. So plenty of reading for you to do yourself at home if you want to explore these things in further detail. So to begin with, we've got this first one, design for your climate. That's a state government production, and that's a good read for yourselves at home. It's specific to South Australia, and some reference to Australia as a whole. But this second one, passive design principles Sun Park, is what we'll be going through to start with today. So I imagine everybody's fairly familiar with the concept of like Earth as it spins around, rotates on its axis, and because it's rotating on its axis within summertime, the sun is fairly much overhead for our latitude. Here, it comes up almost due east, goes fairly much straight over, and then sets to due west because we're not too far from the tropics. But then in winter time, when the sun is over the northern hemisphere, the northernmost tropic, then it's coming up more in a northeasterly direction in the morning, staying fairly low in the sky and setting in a northwesterly direction. So because we have that variation in what the sun is doing throughout the year and its angle in the sky, we can use that to our advantage to say, well, in wintertime we want to get a lot more sun into the building because we want to be warming the building up. And then in summertime, obviously we don't want sun in the building. We don't want any sunlight hitting glass. And it's very handy that in summertime it's coming up due east and going fairly high in the sky and going down to the west. All we have to do there is provide some eaves overhang to the glazing on the northern side of the building to shade it from the sun in summer, and then provide protection on the west and the east. It can be nice during winter time to have some sunlight coming in the morning, sort of from a northeasterly perspective. But typically, when we hit warmer months, sort of from November through to March, we don't really want to have direct sunlight coming into the house in the morning, heating it up too much because it's fairly warm. It's quite comfortable already. So that's for latitude. Oh, so yeah, 45 degrees for H for latitudes up to Brisbane. So anything south of Brisbane, this is a rule of thumb. So H is that distance between the underside of your eaves and the sill of your window. This portion here, to get the best performance out of the sun, that should be about 30% of that distance there. And what is that diagram telling us? So yeah, that's for we're not getting that relationship there with our eaves expressed in this. Sorry, the eaves 45% of H for latitudes. So our eaves width 45% of that height from underside of eave to the sill. So that's a fairly good rule of thumb. If you've got walls facing due north, you can apply that rule of thumb for anything south of Brisbane and get a fairly good result of having no sun come in during summertime and being drenched with sun in the wintertime. So that's a diagrammatic representation of the sun paths that I said earlier. For in summertime, it's heading what's our latitude there? Not sure about that. What our exact location is, because there it's heading slightly south, so that'd be slightly north of the tropic. But for us down here in South Australia, it's coming up fairly much due east and setting fairly much due west in summertime. But then in wintertime, it's more northeast and northwest that it's setting, and it's having a much lower angle in the sky. And that's that same diagram, bit expanded for two-story construction. So for that, you include a shading device over your lower windows to enable that solar access to the building, efficient solar access to the building in that upper story, and then efficient solar access to that building in the lower story. So that's basically just sort of built-in shading for the north. Now, obviously, quite often you've got conflicting desires. You know, so you want to have a comfortable house, but if you're building on the esplanade, for example, you're going to want to have views to the west. If you're building up in the hills, you probably want to have views to the west, and then you know in each individual allotment, there'll be some factors that say this is where we want to have windows. This is why we want to be doing these things, and and of course it's comfort is important, but also livability and the enjoyability of a space is also highly important. So what we've covered there is for glazing on the north. Sometimes you will have to put you know windows in that don't work very thermally efficiently, and so there are other ways you can go about protecting those. So with operable shades and tinting of glass and things like that. So what we're talking about at the moment is fixed shading. Um, Here are some more general rules of thumb for fixed shading louvers. So rule of thumb for Adelaide is 31 degrees to enable winter sun to pour straight through there, but completely stop the southern sun. So that's for a set of louvers that are set out from a building that sit in an angle. Has everybody seen louvers like shading louvers like this before? So it doesn't actually stop any weather from coming down. It's simply as a sun shading. So here's a diagrammatic representation of that louver shading there. So the louvers there on angle allow that sun to pour through in the winter time, but keep the house fully shaded and an outdoor area shaded in summertime. Trees are also a really important factor to consider with your design. So it is, you know, it's very important to have a look at your trees as they exist and see if you can make them work for you. That's the thing about trees, you can't build a tree, they take a lot of time to grow. It pays to think about, okay, can we use that tree? Can we use that tree for our benefit? Because there's not just benefits for us, but it's benefits for the local environment as well. And certain trees are really beneficial in this way. Deciduous trees, so trees that drop their leaves during winter time, are very handy on the northern side of the house because they provide shade that northern side in summertime, but then lose their leaves in winter and allow that sun to pour through. So everybody familiar with both deciduous trees and evergreen trees? Yeah, primarily all of the Australian native trees are evergreen, and our choice for deciduous trees is pretty much limited to introduced species. There are some deciduous trees in Tasmania that are native, but there's it's very few, and they're not really suited to growing in South Australia. So it's one of those things to weigh up as well, whether you're providing habitat for animals and so on, or using an introduced deciduous tree. Also, another thing, deciduous trees are also really good for building bushfire-prone areas as well because they filter embers from when you've got fires, they catch those and they're really hard to get burning. So there are other benefits for that as well, which is a consideration for us up at Shepherd's Hill Road there as well, being close to the bush there. So adjustable shading for east and west elevations, so where we're going to be having windows to the east and the west. So awning blinds still enable a connection to the outside, still enable some visibility to the outside, but will block that sun for fairly much the whole period until it's setting and it's lost its sting. Whereas roller shutters, you know, can be put up and down from inside, so it's very workable for the client, very user friendly, and can shut out the sun quite well. But they're either, you know, they're either open or shut. Either you have connection with the outside, or you don't have connection with the outside. So for keeping cool, passively shaded windows. So think about the sun. Think about not having any direct sunlight onto those windows except for when we want it. Designed for natural air movement. So cross ventilation and convection. Can anybody tell me what convection is? Have you covered that? Convection. Yeah, go for it. Go for it. Well, convection is where you get air moving up. As air gets hot, the molecules become more excited, push each other further apart. That air becomes lighter than the air around it, which is cooler, and the molecules are less excited, so it has greater density. So you have cold air falling down, hot air rising up. That's why you go into in the supermarket and you've got, you know, sometimes, you know, open freezer departments. That's why they stay cool, is because that cold air falls down. And also in some situations where you've got two-story houses with really high roofs, if you go up high on the ladder, you'll actually feel that it's much hotter. The air is much hotter further up than it is down on the ground, and that can be used to our benefit as well for passive cooling. There's I guess typically it's designed in systems that take advantage of that best. So there's things such as cooling tubes, which you can build in under the ground to come into the house, and then have vents high up in your house. So as the air warms up in your house, it migrates up and then goes out the vents, sucking cooler air in. And I spent a bit of time in Iran, in the deserts there, where, you know, people have been building for, you know, for like at least a couple thousand years prior to the advent of electricity and air conditioning. And some of the designs there for using that convection are fantastic in keeping buildings really cool in a really hot environment, where they've got cooling towers that suck out the warm air from the top of the room, and that gets replaced by vents in the floor that draw air from a cellar space underneath the house. So it's pulling in cool air, and that requires no energy or requires no electricity whatsoever. It's just using that convection.
The rammed earth as well. The rammed earth construction out there.
Yes, yeah, and also and the way those with very thick walls as well to provide that thermal mass. Yeah, but also sometimes taking the cooling from thermal mass of those of that earth wall construction as well, to use that to the best advantage. So there are aspects that you can build into houses that will air condition that house for free, which is a fantastic thing, because okay, electricity production is not, you know, it's not very environmentally friendly, but it's, well, there, you know, certainly environmentally friendly options, but also it's incredibly expensive. You know, cost of living, cost of electricity is a very important thing, particularly in South Australia. And so if you can provide, you know, some of those ideas to your client, that's fantastic. But convection is not just about the large movements of air within a building as well. So you've got those large movements of air, but also you get convection happening at your windows as well. As let's say you've got sunlight coming in, it's warming that window. That air close to the window is getting the warmest. That will start moving upwards and then pulling cool air in next to the window and up against the window, warming that air as well. So it will work very much against you, as it creates that that cycle past the window, warming the air. One way we can deal with that is the use of pelmets. And does anybody know what a pelmet is? It's pretty daggy thing really. You'll see them a lot in 1950s and 1960s construction, and you'd even get decorative pelmets above windows, or above your window treatments. A pelmet is where let's say this is our window here on the building. This is inside here, inside the house. A pelmet is this little piece that comes out over top of the window there like that, and often you've got your curtains nestled in there, so your curtains drape down from being nestled within the pelmet. They are more than a decorative feature. They restrict that convection current of air past the window. Let's say we got rid of our curtain, we just had the pelmet there, and we had this motivation for that warm air pulling up like that. As soon as we put a pelmet there, it restricts that airflow, and the air has to go around that. It slows that process down of convection past the window. But also, convection, just putting a whirlybird on your roof also takes advantage of that in a very simple fashion, and a fashion which is of limited benefit. But that whirlybird on your roof gets the hot air out of the top, which means you'll be pulling in cooler air, or hopefully you'll be pulling in cooler air from somewhere else. Also provide ceiling fans to assist air movement. So naturally, when it's hot, we sweat, and that's our bodies maintaining ourselves. To assist in that cooling, if you've got some air movement around, that keeps you cool and keeps you much drier, keeps you far more comfortable. And ceiling fans don't take a lot of energy to drive. They've fairly low electricity use, but also fantastic for mosquitoes and things like that as well. If you want to have your house open in an evening with ceiling fans on, you can keep yourself comfortable and keep a lot of mosquitoes away at the same time. Light colours for external surfaces. You probably recognise that. You go out in the sun with a black t-shirt on, or drive around in a black car, it's going to get a lot hotter than a white car. Same goes for your roof. If you have a black roof in summertime, that soaks in a lot of heat. The reason for that is like dark colours are not reflecting as much light. So our eyes tell us that they see these dark colours and they go, yeah, there's not much light coming off of that, but light is also a source of heat. So as we get that solar radiation coming down, if we've got dark colours are reflecting less of that and absorbing more of it, whereas light colours like white and silver and highly reflective surfaces are reflecting that light, that solar radiation that's hitting them. So lighter colour roofs are better. Now there are issues in that. Obviously, brand new shiny galv sheeting is a fantastic thing, or zinc aluminum sheeting is a fantastic thing for reflecting a lot of light. Councils don't really like that, particularly in hills face zone or in areas like Shepherd's Hill Road. They don't really want those really reflective roofs and light colour roofs. So there's some, how to say, competing interests there. But yeah, we can certainly tend toward the lighter colour roofs rather than the darker colour roofs to make a house more comfortable. Then beyond that, another aspect we have to think about is insulation. So insulation, well, there are limits to insulation. Insulation needs to have space. If we get a an R4.5 bat about this thick, and we go, oh, we've only got this much room to put it in, let's squash it down. That R4.5 bat suddenly becomes like an R2.5 or R3. As soon as we the way insulation works is it's about separating elements that would conduct heat. So stopping that, lots of air in there to stop heat being conducted. As soon as we squash it down, we make it far denser and we reduce its ability to stop those heat flows. But typically when it comes to insulation, it's more a thing of how much money do you want to spend and where is that added benefit going to come from. And also you can't always just thoroughly insulate yourself out of a problem. Sometimes it's better to have better consideration of sighting and orientation and crossflow ventilation and things like that, rather than just simply relying on insulation and also on air conditioning. There are also requirements for suspended floors to be insulated in South Australia. So there's a minister specification that relates to any suspended timber floor must have, I think it's, well, don't quote me on this because I'm going off the cuff, but I think it's R1.5 under your floors to stop that heat transfer straight through the floor. And then also within the National Construction Code, if you follow the deemed to satisfy path for your energy rating, then there are minimum amounts of insulation required in your walls and your roof, depending on your climate zone. Can anybody tell me what climate zone we are here?
Warm temp. Zone 5.
Yeah, zone 5, so warm temperature.
Warm temp.
Oh. So here's a bunch of things all together in the one picture or infographic. Thinking about solar access and correct orientation and shading, providing good cross-flow ventilation. Can anybody think for our site up at Shepherd's Hill Road there, where we'd be getting our cooling breezes from? What direction? What would we be looking for in terms of orientation and providing cross-flow ventilation to that site? Yeah. It's pretty much southerly, like southwesterlies.
Yeah, because that Glenwood Reserve is there. So
So there's lots of trees down beneath. Trees work like air conditioners. Particularly Australian natives are really good water pumps. They get their roots down. They find water and they suck it out of the soil. That can be certainly very problematic for if you're on highly reactive soils and you've got Australian natives right next to your house. They'll suck the moisture out and they'll shrink that clay down. But it's a fantastic thing of free air conditioning. If you've got a reserve that's on the seaside of your house down the hill, you've got to get those breezes coming up. In South Australia, we're quite lucky. Predominant wind direction is southwesterly. That brings in a lot of cool wind in winter time. But during summertime, those breezes are coming straight off the ocean, and they've probably had a fair bit of time on the southern ocean as they hook around and then come up to us. So, and also we have the effect of getting cooling breezes in the evening as well, as throughout the day when we get a lot of sun on the land, the earth heats up. So the earth has less thermal mass than the ocean, and we'll talk a little bit more about thermal mass later. But water stores heat and works as a thermal flywheel better than land does. For anybody has anybody spent any time sort of in the desert camping out at night? You notice how much fluctuation in temperature you get. You can get some like baking hot days and then need to have a really good sleeping bag through the night, because land is not very good at doing that. If you had plenty of moisture in the soil, water in the soil, that works as a better thermal flywheel. But because we have our land here that's getting hot during the day, and then toward the end of the day, that's giving off a lot of heat and helping those convection currents of hot air rise. It sucks in cooler air, typically from the southwest off the ocean. So that wind is those light breezes that are going across the ocean. It's getting that evaporative air conditioner effect from the ocean and then from the bushland as well. And because of that convection current that's created by the land heating up, you get those air movements, and it also works very well in the hills. You get gully breezes that happen as a result of that. So gullies intensify some of those air movements, and you may get a bit of that at Shepherd's Hill Road as well, because we've got a bit of a gully from where that house is. So so for cooling evening breezes, yeah, southwesterly direction is where we want to get all that air flowing through. Also in this infographic, so we've got good roof and ceiling insulation. Talk about insulation. Yes, you want to have a reflective foil sarking on your roof. So it's mandatory for tiles, but it's also mandatory for steel frame as well. If you've got a steel frame dwelling, you've got to have that. I'm not sure what the R value is, but you've got to have the separation of elements. So you've got to have like air cell insulation or something like that air cell insulation between your roof sheeting and your steel purlins to stop temperature or loss of heat straight through those purlins into your sheeting and the condensation that results. So with the steel frame house, you've got to have that air cell insulation. For a tiled roof, you've got to have sarking underneath that tiled roof anyhow, because tiles are notorious for letting drips of water come through. We don't want any of those drips of water coming into our insulation on the ceiling, or even worse, on the plasterboard ceiling. But it's just a really good idea for a sheet roof anyhow, to have that sarking underneath and a reflective foil sarking. If you enable some droop of your sarking, so you've got your purlins and then you enable the sarking to droop between your purlins. So I'll just quickly draw that up for those that may not be able to picture that straight away. So that's our purlins on our roof there, like that. Our rafters and our sheeting goes on top of our purlins like that. That makes everybody, and we've got fascia here with a gutter, etc. Chop our sheeting off. So our sarking goes in between. This is our rafter. Goes in between the rafter and the sheeting, and so it sits on top of those purlins. And you want to create a droop of your sarking like that underneath the sheeting. Now that's for the installed, but also definitely as drafters, if ever you're drawing sarking in, draw it to have a droop, because that's how it works best. If we create the separation of the sarking and the roof sheeting, that roof sheeting, when it's getting really hot from the sun and it's giving off radiant heat from the underside of that roof sheeting, it has this bit of space in here for that radiant heat to come off that and then be reflected back from that sarking. Where we have these points of direct contact, it doesn't work. It just heats up because it doesn't have any space for reflecting that radiant heat. So insulation is your first, how do I say, your first line of defence is straight under your roof covering there. But that's not where the majority of your insulation actually happens in your roof. So that's where you stop a lot of that initial heat coming through. But what we're really interested in is insulating our ceiling, to keep that ceiling, to stop us losing heat into our roof space. Because even a really well constructed, really well sealed roof space is still going to leak like a sieve. Like a tile roof, just there's so much passage of air through it. It's crazy. But even a sheet roof, you lose so much through there. You don't want to rely on your insulation that's up the top. You want to insulate your ceiling as much as possible to keep all that warm in wintertime. But then also your roof space heats up like crazy in summertime, and you want to stop that hot air from coming down through your ceiling in summertime as well. So that's where our insulation is going in a roof space. And another thing, and it's got to do with both convection and separation of elements. So we sort of spoke about separation of elements with the sarking drooping down. If and you notice it from a lot of the earlier architecture in Australia, very high, very steep pitched roofs, creation of a lot of space inside that roof. That enables space for that warm air to go up. So as our warm air goes up to our convection, we've got a lot of space there for that air to go. Once we have a very low pitched roof, where our roof sheeting is very close to our ceiling, our warm air gets trapped up there, and then we keep filling it with warm air, and that warm air comes down through the room. So we're providing less space for that warm air to be. So, and then also you get further radiant heat. As your sheeting is quite hot, it radiates a shorter distance to your ceiling. So, but also by increasing the pitch of your roof and increasing the volume inside your ceiling there, you can provide better thermal comfort as well in a place like South Australia. Then, so we've got good roof and ceiling insulation, lightweight construction to bedrooms. Does anybody know why we want lightweight construction to bedrooms? Yeah. Like, when do we use bedrooms? At night time. We want those bedrooms to, if they are heating up during the day, to get rid of that heat and get rid of that heat sort of, between 7 p.m. and 9 or 10 p.m. whenever we go to bed. For those few hours from when the sun has lost its steam, and we've got a bit of cross-flow ventilation happening in our house from our southwesterlies coming off the ocean, we want to get rid of that heat as well as possible. If we've got big, thick stone walls or something in our bedroom, that's not going to happen. That they're going to be emanating heat, through to 6 or 7 o'clock in the morning. So lightweight construction to bedrooms, if possible. Some of this is relevant to our design up at Shepherd's Hill Road. Some of it's not. There are certain things that if we're doing a design from scratch, we can think, we can do this, and this to maximise our benefit. In a project like Shepherd's Hill Road, we're given a house. It's like, these are the materials you're using. Now, you can have that discussion with your client and say, well, look, if we, add these things here, or if we go with these things there could be benefit, but basically it's fairly much a project that we're given. And then conversely, heavyweight construction to living areas. So that's one thing about that storing of heat. Once again, it's about that thermal mass, using that thermal flywheel effect of getting that heat in during the day, and then putting that out at night in wintertime. Then obviously in summertime, just keeping it all cool anyhow, and that can soak up some of the heat from the room. And yeah, trees and things, protected shaded courtyard. There's a thing that's flying around Facebook a lot. I noticed over the summer, maybe my Facebook, maybe not everybody else, but that infographic about the urban heat island effect, how you've got streets, no trees, 53 degrees, streets, trees, 37. That sort of thing. That's we've got trees. They provide air conditioning through that evaporation of moisture off their leaves. That works like an evaporative air conditioner, but also they just provide shading, and keep the ground and the areas around a house nice and cool in summertime. Yep. Yeah, we have to meet a 6-star energy rating. Now that's if we go for for a separate assessment. There, you can work through the deemed to satisfy approach in the NCC to say we do this to meet those requirements, but primarily, or basically, pretty much everybody goes through that, getting an energy assessment done to meet those 6 stars to save on on all the installation costs and so on. So for that matter, yeah, you've got to meet those 6 stars. You won't meet those 6 stars if you have a very poorly oriented house with no shading and things like that. Yeah, unfortunately, there are plenty of ways around that. I'm not sure I want to really teach you those ways. But yeah, the different building companies employ things like, such as using a reference building, for example. They have that same floor plan, but it's used elsewhere. There's the avenue within the NCC to allow you to get an energy rating for your place by reference to another building which is comparable, and then that comparable, that's a grey area that gets interpreted, etc. And sometimes people go, well, we've built that exact same floor plan somewhere else. We've got that energy rating. Let's apply that here, even though they might be turned around differently and things like that. So it is one of those things that if you're out there and you're looking at a lot of buildings being built, sometimes you really wonder, how on earth did this pass energy assessment? Excuse me. Yeah, you get that, but there are various reasons why that happens. And also, when you've got multi-residential developments, it's about an average star rating as well. So I had a look at a unit it was in Mawson Lakes, and if I was to design a solar oven, I would not have had to do much more. It was massive windows facing west. It was a long, skinny apartment that you just get in the evening. You just get so much heat coming in there, baking everything inside. And you think, how on earth does that make it through? Well, it makes it through on the back of the other units within that development. So other units will have much better orientation and design. So there, yes, some very poorly oriented houses with bad shading and well, very poor design does make it through for various different reasons. But in the main, the answer to that is no. It doesn't. Yeah, it's not complying.
Is that
Yeah.
plus also taken into the consideration when we are doing the energy rating?
Are plants taken into consideration?
Is that plus?
Yes. Yeah. So what you have to do with the person carrying out the energy rating assessment is you provide them with information about the trees which are there. So you say, what species of tree it is, whether it's evergreen, deciduous, what height it is, what distance it is from the building, so they can go, okay, well, it's providing shading for this time at this point in time. What's that? Yeah. Well, don't know actually. I don't know whether energy raters will. I assume they rate a building as as it is at that given point in time. They don't know if that building that tree is going to grow up to fruition. Whether yeah. But I guess there's so many assumptions they've got to make. That's probably a much better question for somebody who does energy rating assessments to see, how do you deal with trees, because people can chop down trees, people can plant trees. Trees are going to be different today than they are in the future. Not sure. But certainly things like awnings and blinds and curtains and things like that. If you specify them for your energy rating, it means you've got to put them in to the house. Because if you don't end up putting them in to the house, well then that energy rating doesn't apply and the building is non-compliant. Also, other aspects for thinking about orientation of the house and design of the house. So once again, our Shepherd's Hill Road property, we've got given a floor plan. there's not that much we can do to that. We're not going to go, all right, well, let's pull this whole thing apart, put bedrooms here, put living areas here, and things like that. We get this floor plan. But one of the things that's also important to think about with your design is to have your sleeping areas to the southern side of the house and your living areas to the north side of the house. Because the north, you can maximize your solar gain. In wintertime, those areas can be kept warm. And also, it's quite, it's a bit personal preference, but quite often people sleep better if they're cooler. So cool areas for sleeping, and then warm areas for living. And this is another diagram here showing what I spoke about earlier with convection, with that hot air rising and pulling in cooler air. So that's more of a tropical design, which suits, has suited a lot of people for centuries. That live in the tropics, to have a lot of ventilation, roof ventilation, use that convection. I guess because prior to only probably not even, I don't know how long have air conditioners been about, probably since the 1960s or so. So it's really very short space in time that we've actually, the air conditioners have driven our design of buildings. Prior to that, it was like, how do you make do with with the building and the climate? That sort of thing, unfortunately, doesn't meet the energy rating assessment criteria very well, and also doesn't meet the deemed to satisfy requirements within the NCC, because the energy rating assessment is very much about encapsulating a house, stopping uncontrolled drafts, so that climate can be controlled very easily. I'm certainly I'm very how do I say it, partial to such a design. I think that's a lovely sort of thing to be able to get that convection happening, particularly in the evenings. But it doesn't meet our energy assessment aspects very well within the NCC, because I guess the NCC has to set down the ground rules for everybody, and when you get a one size fits all situation, you get some situations that don't fit very well into that. So that's where you've got an apex vent on the roof. So the apex of the roof is vented. Other forms of ventilation, and I guess the idea started with, well, has everybody seen Dutch gables on a house? Does anybody know what a Dutch gable is? Yeah, you probably built them. Yeah. Yeah, so the original idea of that Dutch gable, having that small triangular element which is open, was to provide ventilation in that Dutch gable at both ends of the Dutch gable, to enable breezes to pour through a roof and pull that warm air out. So suck all that warm air out and enable cooler air to come into the building from underneath. So the reason they're called Dutch gables was because they were first used in South Africa by the Dutch settling in South Africa from a fairly cool climate. South Africa, quite a warm climate, and one way of getting that passive air conditioning was via the design of the Dutch gable. A lot of your Dutch gables, or probably 99% of your Dutch gables built onto buildings now, are just aesthetic. It's about creating some articulation in the roof space rather than providing that ventilation. But some Dutch gables you see about the place have those little vented louvers in the top still working like that. And as Sarika mentioned earlier, plants are cooling. We've got the reserve down below. So design planting to funnel breezes into and through the building, filter strong winds, and exclude adverse hot or cold winds. Does anybody know where we get our hot winds from in South Australia? North. Yeah. Yeah.
That's the direction.
Yeah. So yeah, straight from the north. If we've if we've got northerly breezes, we know it's going to be a really hot day because the air hooks around, goes over Victoria, New South Wales, comes back down through Central Australia, Lyndhurst and whatever, and it's picked up a lot of heat by that time, and warms us up. So think about shielding from those northerly breezes that we get here. And some links there to further reading, although there's a lot of reading which has been provided on this Learn page here. So that was the passive design principles, sun path section, and there are some other things for your reading at home. So design for your climate's probably a fairly good read to brush up on some of these things. This one here, this is a link from Gosford Council. I don't know. I think Gosford is it in New South Wales? I haven't even looked. It is in New South Wales, Central Coast. Yeah. So that's so it's not really applicable to us here in South Australia, and certainly not applicable for our project there. But it's good to grab some of these resources from other places around the place. Particularly, there's some really good info sheets and so on that come out of state government in Queensland about a lot of building, etc. This one, it takes you through their requirements and what they require in terms of consideration and information in relation to building environmentally sustainable, affordable housing. And so there's some really good ideas in there. Also beneath that, this one is really cool. Muck around with it. That's an Excel spreadsheet which is set up for doing, I guess, a preliminary energy assessment. It's not an energy assessment. You can't go out and start doing energy assessments for yourself or for others based on that spreadsheet. But it gives you a bit of an idea. So if you plug your information into that, it tells you, are you doing well? Are you not doing well? What areas can you improve on? So have a muck around with that spreadsheet as well, if you have plenty of spare time. Well, actually, no, you won't have plenty of spare time if you're doing this subject. But have a look at it and keep a copy of that for giving you some idea later on. Also, what we're going to have a look at now is, once again, the second file in the series. So insulation, glazing, heat flow. Some of these things we've already touched on this morning. So when we hit those, we'll brush over them. But as I mentioned briefly before, you can insulate your way out of a bit of trouble. You can, if you've got aspects of your house which have been incorporated for various reasons that don't create a very comfortable house, insulation can really help you out there as well. But also the properties of the glazing can really help out as well. So glass is a notoriously bad insulator. It lets so much heat in and lets so much heat out that at times it can be real curse. Yeah.
With the zoning for the climate, would Australia's zoning be different to, say, Europe's zoning?
Oh yeah.
So then do they go off the same zoning, go lower than that, or?
I don't know. I get what you're asking. No, I don't know if there's an international standard and an international way. I probably, if I was to have a guess, I'd say no. Because we've got the National Construction Code and we have the climate zones for the National Construction Code that have been worked out for that. Yeah, certainly, it'd be a very interesting thing to know. Yeah, yeah, because that'd be a fantastic thing if there was a global climate zone, yeah, accepted framework that you can go. All right, we're climate zone 5 here in South Australia. We're also climate zone 5 in parts of Italy or South Africa or whatever. That'd be a really handy thing to know. Yeah, but no, I don't. I've never explored that. So yeah, so glazing, glass is really bad at keeping heat in, and you can double glaze, and double glaze certainly improves things significantly, but you're still not going to get anywhere near the insulative value from a pane, an area of double glazed window as you are from a wall. So your insulation is always going to be far better with a wall, but there are various different properties from that glass that you can consider in making your choices about glass. And one of them is insulation. So just a bit of a generalized view of houses. In wintertime, you're losing 20 to 35% or 25 to 35% of your heat through your ceiling, 10 to 20 through your windows, 15 to 25 through your walls, a bit through your floor, and a bit through air leakage. Now, every single house is going to be different, and that's why diagrams like this, they provide a little bit of a guide, but yeah, each their own. If this was a suspended timber floor house, well then that percentage would be much higher, and also if it was a weatherboard clad house that didn't have much insulation, well then your air leakage is going to be far higher than some other situations. Or your air leakage in a brick veneer house is really quite high in relation to a solid clad house as well. Yeah, so a lot of variance there, but as a general rule, it's okay. And then in summertime, your heat gain 25 to 35 through the roof, and much more through your windows, 25 to 35 through windows than your heat loss in winter. And then yeah, pretty similar for your air leakage. So places where you can get a bit of heat flow
That way.
happening in here.
Yeah.
So talking about gaps and things like that. Now that's so for the energy rating, and for those of you who've seen things on grand designs where people completely seal up a house and do that air exchange test. A lot of that thinking is about containment of a space and creation of a an even temperature within that contained space. So that approach, that thinking about energy efficiency, doesn't like air leakage very much, and that is certainly very important concern if you are going to be air conditioning or heating a space. Is that air leakage, and also if you get your orientation really good, well then also you want to be minimising your air leakage, because you've got your building performing really well in a passive sense, and you want to contain that. I won't go through. What's that? Answers. So heat flows by 3 mechanisms. We'll go through that quickly. Conduction. So that's when you've got connection. So I touch a hot plate with a steel rod. Eventually, that's going to get to my fingers through conduction. So various different materials conduct heat better than others. So it's pretty much a no-brainer. If I touch that steel hot plate with a piece of timber, I'll be able to keep my hand there for a lot longer time, because timber doesn't conduct heat in the same way that steel does. Convection, that's air moving around, and then radiation, that's the heat that you get from elements. So let's say we've just got a sheet iron roof above us, no insulation, anything. We're standing inside a shed. really hot sunny day, we'll get a lot of radiant heat off of that roof, so the heat radiates down. Also, we don't have any in here, but you may have seen it out at cafes, etc. Heaters that are just these black strips. You guys seen those? Yeah, they're radiant heaters, so they just provide that radiant heat to keep you warm. In general, heat flows from elements or objects with a high temperature towards ones with a lower temperature. So heat is about molecules being excited, about them moving around. They'll excite other molecules and transfer that heat to elements that are cooler. So heat will flow out of a building if the outside air is cooler, etc. How fast the heat flow depends on the temperature difference between the two sides. So if it's hot outside, eventually your house will get hot inside, and that all depends on how quickly that happens. Depends on the resistance, or the resistance to transmission of heat through your building elements. So that's so that resistance is measured in K values, and then those K values are multiplied by the material thickness to give you an R value. What's important for us to consider if we're going down D to satisfy, or if we're comparing forms of insulation, typically it's R value. We're concerned with R value, so we're thinking of R4.5 in the roof, R2.5 in the walls, R1.5 for a suspended floor. So we think about those R values for our insulation. And then sometimes you've got practical limitations. If you're doing a cathedral ceiling, the amount of space you've got between your roof and your ceiling, then you start thinking about, okay, well, I've got to get this R value of 4.5. How can I get that into this space? Then you start thinking about materials that have a high K value. So, okay, if we've got this sort of boarding product or this that has a very high K value, that means we can get a lot of R value with a short space. So typically, it's not a measure of comparison unless you're starting to think about thicknesses of materials. Yeah, keep moving through that. So heat flow, the conductance of various different materials there gives you guide. So as I mentioned before, steel is really high. Steel transmits lots of heat, and that's why we have to have that air cell insulation on top of or on the outside of a steel frame to stop that conduction of heat. Glass, significantly lower than steel, but the thing is, glass is typically very thin. So we've got a very thin piece of glass. It's not it's not having to resist temperature difference for very long. And then your other various different elements. So concrete transmits heat slightly better than glass does, but the thing is, we've typically got really thick concrete elements, and that is the difference. But also, I think it's important to draw that distinction between concrete and then fibre cement sheet as well. So fibre cement sheet uses cement powder in it, but you've got a lot of fibres in there as well that don't transmit that heat nearly as well. So your fibre cement sheet is far less than your concrete. Now we'll go through these fairly quickly. It's more of a point of interest than anything applicable to what we're doing with our design up at Shepherd's Hill Road. But has anybody ever heard of a trom wall? It's basically it's a way of taking passive solar design and thermal mass, thinking about how they both work, and incorporating that into a house to get the absolute most out of that. So, maybe that's a good. Yeah, no, this is a better diagram for showing it. So we understood before, in terms of passive solar design, that's about orientating the house with glazing facing north and adequate shading over the top to ensure that there's no summer sun getting the building elements in summertime, but lots of summer sun during the winter time. And we then use that solar access to store heat in elements that have a lot of thermal mass. So a concrete slab is a really good example of that. If you get all your sunlight pouring onto your concrete slab, it takes in that heat during the day in winter time and then gives it out during the night. So it's keeping your house warm in the night. But you can also, rather than just have your floor elements, which also lose heat, like as your slab heats up, it loses its heat to the ground as well. Like it gives the heat out to the room, but also loses it to the ground. If you were to put in a solid masonry wall behind that window, you enable that solid masonry wall to take in that heat during the day and give that out at night time. But then you can also use convection by having ventilation at the top and the bottom of that to your benefit as well, to be pulling cool air from in your room and pumping it out back as warm air into your room and creating that cycle. So such a design can work very well for a situation whereby you think, okay, to make the house comfortable, we want northern glazing, but really we don't want to have glazing here because we're going to be looking right at the neighbours, or or there's something we don't want to be looking at on that northern side. What you can do is you can provide that glazing and then have a solid masonry wall to act as your thermal mass, so you're still gaining the benefits of it, but you're not having the views that you'd rather not have.
What you're saying is, can you add that glass wall on any side?
Well, you want to have your glass wall on the northern side. But if you're going to do a trom wall, yeah, it works on the northern side.
It doesn't work on the other side.
Well, on your say in a situation like sort of northeast or northwest, there might be some benefit to it as well, because in the morning you can get that trom wall heated up, and then in the evening you can get that trom wall heated up in winter time, but still keep that relatively well shaded for summertime. But you really don't want to have thermal mass or this sort of situation happening on an east or a western wall, because typically they're going to be most exposed to that sun during summertime. When the sun's coming up in the morning from due east, it's going to be heating up that wall and heating up your house in preparation for the hot day ahead. It's not what you want. On the western side, it's going to get blasted by that heat as the sun is setting, and then heat up your house summertime at night, which is also what you don't want. So east and west, I'd say certainly no. Northeast and southwest, yes, possibly in a cooler climate where you can control the shading. You can use it to your benefit. On the southern side, well, you're not going to get any sun on the southern side, really. You're going to get some radiant heat. You're going to get reflected light, so light bounces around all over the place. You still get light coming from the southern side of the house, but you don't get that solar radiation. So there's no point to doing it on the southern side.
How close is the wall bead to the actual windows itself? With the gap and everything, and that being, especially on the right hand side where it's fully enclosed, that would be a fire risk.
A fire risk?
Yeah. Because the fire would essentially, if it would burn through that glass, in between two bits of glass, you've got a giant pot of air causing.
Oh yeah, the chimney.
Backdrop,
Yeah.
and you've got another whole section of air ready to go for another backdrop straight away. If you had a fully enclosed one.
Yeah.
Can you see out of
Yeah.
glass?
What's that?
With that wall there, it's hard to see through the glass.
Yeah, it looks like this. On those things. It's just a wall behind the glass. The whole point
Yeah.
is the glass is amplifying the winter sun on the wall to make it hotter, and
So when
then
you
the
were
heat
saying that
radiates
it's
through the whole
not
day.
used, how is it used?
Yeah, exactly. So if you have a situation whereby, say, you want to have glazing on the north for making a comfortable house, but you don't want to be looking directly at the neighbours. I've been through the design process for exactly that scenario with a place where directly from the northern side of the building you're looking at the neighbour's place. You're looking right there. They don't appreciate it, and occupants of the house don't appreciate it either. Particularly if it's sort of fairly rough sort of outlook. And so there are some situations whereby you might say, well, to have glazing on our north is really the best thing for us to create a comfortable house. We want to have that, but we don't want to be looking at that. That's where it can also be handy for you.
Is it very common? Like, have you seen many designs like that before?
No, it's not very common at all. No, it's fairly rare. A lot of the um, there are expenses involved and there are sacrifices involved in designing passive houses. For something like this, you're not. One of the difficulties is you're not going to have your standard slab underneath. If you're imposing a massive point load on a building at that point, you're probably going to want to have a footing beam running underneath that. But then if also and if that roof is taking your roof load and so on, yes, you can redesign a slab to have a substantial beam there, and then you may only need a very small external beam. I know that's up to the engineers to work out. But one thing you can very confidently say is you're going to have a different slab or an abnormal footing system for that. And typically, as a general rule, when you step away from normal, you start stepping into expense. That's a general rule. It doesn't always have to be that way, and that's what smart design is about. But yeah, a lot of these things, we don't see. It sort of creeps into people who are more enthusiastic about that into their designs. But yeah.
Modular glass windows facing what the views are.
Yeah.
Does that having that amount of windows on that north side affect everything? How do you
Well,
get away with that?
Yeah, typically if you get your shading correct and you're using the thermal mass correctly in your building, that can work as a really good thing. Yeah, where if you've got your views to the north and you've got lots of glass to the north, but then you only have very small amounts of shading on your glass, it would be detrimental, because in the summertime you get a lot of heat onto your slab also. Or also if you've got a lot of glass but you're a suspended timber floor, there's no real thermal mass to the building, it can also be detrimental to you as well, because you'll be getting a lot of that heat, that sunshine in during winter time, but then because you've got so little thermal mass of your building fabric, you lose all that heat very quickly, and then come 11 o'clock at night, the house gets quite cold, and then by the time it's 6 or 7 o'clock in the morning, you've got a very, very cold, uncomfortable house, even though you've got your orientation and your glazing correct. So these things, they always work in concert with each other. So you've got to understand how that passive solar design works with the thermal mass and how it works with the shading. But then also, how are the benefits from that and benefits from the thermal mass contained within the house? So how does that insulation work?
Couldn't you use double glazing?
You could use double glazing. So double glazing, like your argon filled double glazing, I think the maximum R value you can get out of that is 1.5. So yeah, certainly that's better than just single glazing, but it's not as good as a wall where where you can typically get R2.5 to R3 out of a wall. So yeah.
And the expense of it is crazy.
Yeah, but cost of windows are coming down as well as we get more manufacture overseas, and that's getting far easier as well. But yeah, still Windows much more expensive than a wall. Walls are cheaper to build in comparison. But yeah, so there's that option of tron walls, either tron wall that allows convection currents through there, or a tron wall that that just simply works for thermal mass. Has everybody, actually I can't think of what they're called, earthships. Has anybody seen an earthship before? So it's it's taking a lot of these principles and just applying it in more of a fundamentalist fashion to create like the zenith of passive solar design. And and a lot of these earthships incorporate elements like that. And I just mentioned earthships. That's more the earthship sort of design, or if you're designing for really cool climates and in Europe, for example, typically you'll have a window on a slope, because heat gain in summertime is not such a problem. In South Australia, we do have to think about heat gain in summertime. Heat for us in summer, is something we want to avoid. I think we've covered that fairly well. Well, this diagram shows some comparison of what thermal mass enables. So our green line is the internal temperature of the building, and we've got internal temperatures with low thermal mass, the lighter grey, and then the dark external temperature. So if we're not using thermal mass to our benefit, the temperatures in the building are going to fluctuate like this, whereas if you're using it to your benefit, it's far more like that. Where thermal mass can be a real curse is like weeks like the week we've got ahead of us now. It's like 37, 37, 37, 37, 38, 39, 40, 40. It's it's going to be at the end of that, I know my house is going to be stinking hot. Like I've got an old cottage with walls about this thick. Nothing you can do about it. It will heat up. That thermal mass will be a curse at the end of this week. But if used appropriately, it can be of a real benefit, and used judiciously. Also, just quickly we spoke about roof colours before. Lighter coloured roofs are better for reflecting that heat. Also works the same with your thermal mass as well. If you've got a solid masonry wall that's painted in a matte black, that's going to absorb a lot more heat than if you paint your thermal mass wall in a gloss white. One way of using thermal mass to our benefit is by reversing the notion of brick veneer. So you'd all hopefully be very familiar with what brick veneer construction is. If you live in South Australia, you work as a drafter, or you work in the building trade, you've got to know what brick veneer is. You've got to know those details. That's the way most stuff is done, whether it makes a lot of sense or not. But what brick veneer does, your traditional brick veneer, is it puts all of the thermal mass of that material on the outside of the wall, and then all your lightweight stuff ends up being on the inside, which is kind of the reverse of what we want to do if we've got all our shading and orientation correct. So if you do have your shading and orientation correct, you can get some of that thermal mass inside the building by actually reversing the way that you build the brick veneer wall, by having your load-bearing timber frame on the outside, then your insulation to insulate from the heat that'll be coming onto that wall, and then you have your brick veneer on the inside providing thermal mass to that.
Is that common?
What's that?
Is that common?
That's not common either.
No.
Yeah, I've seen a few places. There was can't remember his name. There was a builder who was sort of really getting it going, whereby it wasn't about using bricks, but it was about using like a plastic form that that you pour concrete into. So he was building. I saw one of his places down at Morfett Vale. Yeah, Morfett Vale. He was building there, where timber frame, and then like a series of brick ties into this plastic formwork that he fills with concrete to have a concrete internal wall to do that very rapidly. But yeah, unfortunately, I don't think he built many places. Once again, when you step away from normal, because building is such a major investment for people. Typically, and this is not at all being derogatory, but you have a population which are like a lot of people who are not really well educated in the space, because they got if you're not working in the building industry, if you're not designing, it's not where your thoughts are typically. But because people are making such a massive investment based on on a coming from a relatively low education base in that, they'll be very scared to step into new technologies. And they go, oh, I've seen those grand designs where those people did that experimentation stuff and they lost a lot of money. And so, and that's very reasonable. And so a lot of what we do is in that context. And you can have fantastic ideas, and and eventually the economically viable ideas rise to the surface. When it's at the cutting edge of technology or pushing the envelope, it might be difficult to get things started off, but eventually they will. And I think we'll see more of this, flowing through in future. But currently, no, it's not common. So we talked about conductivity of materials before, and I spoke about steel frames requiring that air cell insulation. It's about thermal bridging. So thermal bridging is important for all of your building fabric, including windows. If you are spending a lot of time and consideration and money on producing a house which is thermally comfortable, and the cost of going to thermally broken window frames is not too much extra, then then I can really see the sense in doing that. So thermally broken window frames, that's about ensuring that the window frame that's on the inside of the house has some sort of thermal break between the section that's on the outside of the house. So you have like a plastic element which is non-conductive between those two. So you're not transferring heat from inside or outside of the building. So these are thermally broken windows. And yeah, once again, not really common in building, but this is one of the things that is very easy to quantify what it costs. You go to your window manufacturer and say, what does it cost me for your standard frames? What does it cost me for thermally broken frames? And they'll say, oh, it's 5% extra for your thermally broken frames. You go, okay, $10,000, we're looking at $500. Do it. Like, that's an easy decision for people to make, and this is something you see coming much more into construction. There's a place we were looking at getting windows from that specialise in, well, they specialise in doing double glazing. That's mostly what they do, but by and large, the majority of their window frames are thermally broken, because that's their biggest sellers, the thermally broken ones. there's not a great deal of price difference between them as they start becoming more and more common. So I mentioned before that glazing has various different properties, and we can select the various different properties in our glazing as well. So, yeah, it's fairly wordy, this slide, but we can go through sections. So, if we had large windows facing west, we're building a place on the esplanade, we'd probably want like tinted, toned, or reflective glass there. So we still get the views out to the ocean, but when the sun is setting in the evening, it's not baking the whole house. So that's called low SHGC, so solar heat gain coefficient. Let's say we're building a place in the hills where it gets quite cool, but we've got some amazing views to the south. We want to capitalize on those views. We want to maximize the insulative value of that glass because we want to capture that. We'll use a low E glass. Low E means low emissivity, so it's got a higher resistance, a higher R value to it. So you'd use double or triple glaze with argon filled. So argon is an inert gas. It's not very conductive, so it doesn't conduct the heat. And yeah, so for a situation like that, you'd go low E glass. So talking about our place on the esplanade, we want like low solar heat gain coefficient. If we were putting the glass on the northern side of our house to get that warmth in, to get that solar radiation through, we'd want very high solar heat gain coefficient. So SHGC can be a benefit. Like you can choose low or high depending on your location within the house. Like emissivity, like your low E glazing, that's generally a good idea anyhow wherever you are. Helps maintain that temperature in your house, gives you far more control over that. And also, so with your window frames, you can have thermally broken window frames, but then you can also choose to use materials that have lower conductivity as well. And it's all sort of a play off in in what else you want. But timber framed windows, they don't conduct as much heat as your aluminium frame windows. They're more maintenance, so they need to be painted, and eventually 10 years down the track they need to be sanded and things like that. You've got that maintenance, but they transmit less heat, or they can be draftier though than your manufactured aluminium. Aluminium can be extruded very neatly and formed very neatly with incorporation of rubber seals, much easier than timber can be. But yeah, you've got aluminium, timber, UPVC windows, and they're actually relatively common. Like PVC window frames, they don't really stand out too much from your aluminium. It can be hard to pick. Tricks with that. That stuff we've covered already. Here's some comparison with various different scenarios about heat loss through. With and also when we're thinking about glazing, there's another aspect that I think we haven't really touched on. It's about the use of lights within the house as well. Now that's of less importance now because we've got LED lights which use very little electricity. So this has become less of an issue. But for the National Construction Code, you have minimum requirements of light and ventilation. Put really simply, your light has to, your space of window has to be 10% of your floor area. So we've got 10 square metre 10 square metre room. It's a very small room. We've got 10 square metres just for ease of calculation. That means we need to have 1 square metre of window for that 10 square metres of room, for habitable rooms. That doesn't include toilets and toilets, bathrooms, laundries, things like that. But for your habitable rooms, it has to be 10%. And then you need to have 5% of that floor area as ventilation. So if you've got 1 square metre of window, half of that window has to be operable to provide that that ventilation. So you've got minimum requirements within the NCC for light and ventilation for your windows, but also of how to say it, like a lighthouse. It's also, it's a very nice, it's very like, it's, you know, that's comes down to individual preferences as well. But if we just look at design trends in general, people like to have a lot of light, they like to have a lot of natural light. They like to have that pouring in into the house and not rely extensively on artificial light. And then, of course, yeah, your requirements for ventilation by the NCC, but also by making a comfortable house. And one way to think about it, if you really want to get nitty gritty about the figures, is you can, you know, it's very simple to model. Okay, these are our costs today. Weigh that up against the predicted energy costs later on, and say, okay, currently we can borrow money at close to 4%. That's so if we're spending extra $10,000, we're paying 4% interest on that a year. That costs this much per annum in comparison with if we had an increased electricity bill of X amount projected forward. So these calculations can be done. They're not too onerous, and that can also, if you're that way inclined, you can do those sums with your client. That also helps your case as well, or increases your value as a designer or drafter to be able to provide that. Yeah, I think we've covered everything fairly well. So there's various different tools for calculating the requirements of insulation. However, it's also not too difficult to go straight into the NCC to go, this is my climate zone, this is the insulation that I need. So, your potential savings. So if you're going to go through that that thing of providing that cost comparison to your client, there's those in the calculators. I think we've covered this fairly well already, so we'll go through it fairly quickly. Talking about the system R values of walls. So a wall provides much more insulation than a window. And then once again, if you minimise the thermal bridging, then that insulated capacity is increased once again. Oh, one thing we didn't mention is keep moisture away from bulk insulation, or its performance will be reduced. So, you know, if you're wearing a wet jumper or a dry jumper, obviously the dry jumper is going to keep you much warmer than the wet jumper. So this is talking about scenarios where you've got a cathedral ceiling or raked ceiling that follows the roof line closely. It's very difficult to insulate and very difficult to stop that transmission of heat because you've got so little space. a lot of connection between elements. This is showing us the importance of having that airspace between an external element and the reflective foil. So that's essential. This is a detail here showing where you can use cavity board insulation. So for cavity masonry. I hope everybody in this class is down with using the term cavity masonry as opposed to double brick when we're talking about 2 leagues of brickwork with space in between. A lot, typically you'd be talking to people, they would go, "Oh, I have a double brick house." Very few people have a double brick house. They have cavity masonry. That's where you've got 2 leagues of brickwork with cavity in between. When you've got that cavity in between, then you can do something like this cavity board insulation in between the two, and your brick ties go straight through that with little retaining clips on that. That works. I guess you're getting your benefits of reverse brick veneer in that you've got masonry on the inside of your house providing that thermal mass, but then you've got your benefits of a brick veneer house, which are an external skin of very durable materials on the outside. Oh, can anybody think of one important thing that we haven't covered so far in energy efficient design? Another thing, it's not so much about the design of the house and the ongoing costs and benefits of that, but it's more simply applicable to being environmentally conscious is the embodied energy of materials as well. Yeah, click through that. Yeah, we've covered all of those. Oh, actually, go into those. But yeah, that's another thing we'll cover a little bit further on is embodied energy as well. And so we always have to think about that in concert of what we're doing. So, for example, a concrete slab. We talked about concrete slabs before for our thermal mass. We get our glazing right. We get the sun on there. It's providing a lovely, beautiful temperature house that we don't require much input of energy. But the thing about a concrete slab is it requires a lot of energy input to bake the cement powder, to create the concrete, to bind all of that together. So there's always going to be that interplay of embodied energy versus energy use into the future as well. Some of that embodied energy is reflected in prices because energy is expensive. Making bricks is now far more expensive than it used to be. Bricks are becoming more expensive. But I was reminded of that when we, looking at this double brick wall. What we end up, okay, yeah, there's some thermal benefits in that, but there is also a lot of embodied energy in that. Baking those bricks, getting a clay brick and firing it at whatever 1,000 degrees, Celsius to get it to vitrify. It requires a lot of energy. So various different types of insulation. So I spoke about air cell insulation before. Actually, I could grab some examples of insulation if you like. Do you guys need to see examples or would you like to see examples of insulation, or you've pretty much seen, what I'm talking about when it comes to insulation?
I wouldn't mind seeing some examples.
Wouldn't mind seeing some? All right, I'll just go quickly grab some from the storeroom because it's right here. But yeah, typically the rule of thumb is when it comes to insulation, your cheapest form of insulation is going to be your bulk insulation, your bats. They're typically going to be much cheaper than any of these things. So if you can get away with insulating your house well with bats, yeah, do that. Also, yeah, there's loose fill insulation as well, which is typically recycled paper, so paper which has all been mulched up, and then that gets pumped into walls or ceilings as well. You probably would have seen the ads for Cool or Cozy on TV. That's one of those loose fill insulations. Yeah, covered that. Oh, what we didn't mention is wool insulation, so natural wool insulation, fairly expensive. Typically, it's not used because of that, and it also has to have fire retardants put in it and stuff to stop rodents eating it as well. So, although it's a certainly a a good material in terms of its life cycle analysis, and it can be turfed out without being too environmentally damaging. Yeah, it's expensive. And polyester insulation made from plastic bottles. Um, that's the extruded polystyrene that we saw. Yeah, so that's insulation. The last thing we have to look at today, or for this, it's about embodied energy of materials. So, yeah, possibly something that you can. It's not so much about building design, but about building management and sort of a bit of a holistic, life cycle analysis of the building. So make use of existing materials efficiently. Well, I guess that plays into design very well. Can anybody think what things we need to think about to be using materials efficiently? One really important thing. Yeah. Also, so cost basically. Yeah. If we can use materials efficiently, our costs are way down. We're far more competitive in that, and you see that with. Although, yeah, I won't give it away. I'll give someone else a chance to get this. Now, what's that? Oh yeah, you got to store stuff correctly to minimise wastage on site, etc. Yeah, there's all that sort of wastage on site and wastage that happens as a result of poor planning. There's something that we can do as designers when we're designing a place. Yes, yep, certainly using materials that. No, the thing I was getting at is, think about your ceiling heights. What are our standard ceiling heights? If anybody knows that.
2700.
Yeah, we've got 2400, which is the really low ones, 2700 and 3 meters. Why do we have those ceiling heights? Why don't we go, 2470, or why don't we go, yeah. So you get plasterboard sheets in 1200 by 2400 or 1350 by 2400, or some sections 3 meters long. So a lot of our materials come in those specific dimensions. Yes, we could say, oh yes, I want 2780 high ceilings, and then your plasterboarders are going to have to get some, two 1200 sheets, and then cut off, 370 mil of a sheet, and then they'll cut off 370 mil on the other side because they want to have those neat formed recessed edges for where they don't want to have a cut edge exposed partway through a wall. So if you're going to do that, then you have this 600 or 700 mil slab of plasterboard that goes to the skip. The reason we have like the reason plasterboard comes in those dimensions is because brickwork, the size of our bricks, 230, 76, 110. When you start building walls, you end up getting into increments of 1200 millimeter or increments of 600 mils going up and going out. That means your brickwork, your heights of your brickwork work very well for these ceiling heights, which means that dictates the size of your sheets for your walls. And when you purchase timber in 6 meter lengths as well. So there's all those things about the standard size of building materials that will dictate the efficiency of a build. And to go, okay, well, if we understand the size of a brick to ensure that we're not chopping too many bricks and throwing 1/3 of a brick away. Like brickies don't like to cut things in 1/3, 2/3. They like to cut it in half or not cut it at all. Because if you cut it in half, then you've got another half to use elsewhere. So if you're cognizant of those things, the size of your building materials and how to use that efficiently, then you're just going to have little or no wastage. And then so after thinking about that efficiency, about minimizing your wastage, then you can think about, okay, well, what of those building elements is not such a bad thing to waste? And probably the thing that's not so bad to waste is pine or timber. Timber's fairly cheap. You know, if you're going to be going like, okay, well, I'm going to be inefficient, you know, maybe being a bit inefficient with your timber is probably the place. Beyond that, if you're going inefficient with concrete, well, then you end up just having these big, big pats of concrete that have to happen. Concrete trucks, if you're close enough to where they're operating, they can take them back and they make those great big concrete blocks and, etc. But you probably don't really want to be wasting concrete. It's messy, blah, blah, blah. You don't want to be wasting paints. Don't really want to be... you can waste a bit of roof sheeting. Roof sheeting can all be recycled. But yeah, you don't want to be wasting bricks and Besser blocks and things like that. They weigh a lot, and getting rid of them in the skip. And you definitely don't want to be wasting plasterboard. Plasterboard, when it breaks down off gases, it's not very environmentally friendly. So minimise waste. And think about the environmental impact of those materials as well. So what has a really high embodied energy? So aluminium, massive embodied energy in aluminium. You don't want to be wasteful, or actually aluminium is expensive anyhow, so you don't want to be wasteful of aluminium, and if you've got spare, you recycle it. Life cycle performance. So mentioned before, concrete has a very high embodied energy, but it lasts for a really long time. The Romans were building concrete thousands of years ago. It's still around. So while yes, there might be far more embodied energy in a concrete slab today, it will last a lot longer than a timber floor. And certainly, if any of you know the standard sort of detail for a platform timber floor, where you've got floor joists and then your structure floor on top of that, your 19mm chipboard floor that goes straight on top of that, and then you build your walls on top of that. What happens when you get a leaking bath or leaking shower or something like? Well, actually, let's not talk about wet areas. That's a whole new can of worms. But okay, we'll talk about water damage from something else. Some water making it into your walls from bad fascia or something like that, and that particle board swells up because it's underneath your walls. You can't just easily go, okay, we'll replace that bit, get rid of it. I had a job whereby the exact, well actually no, I had a few jobs where it's been that exact scenario where chipboard is underneath walls. It's game over. Knock it over and start again. Now it's incredibly wasteful. And so to think about all of those things, I guess maybe a benefit to clients, but it's also more about your environmental consciousness and your thinking about that wastage and the life cycle analysis and performance of these things. Recycled materials. So to help reduce a lot of the waste, that's something that bugs me. I don't know if it bugs a lot of people. Is watching demolitions and seeing some I like timber, and sometimes you see just some excavators with the grabs on there just going into a roof, goes and some lovely big Oregon beams and whatever just getting ripped out and destroyed. But the reason that happens is because the demolition is very dangerous. To have people in there deconstructing something, you really have to think about how that's going to play out. If you go chopping bracing, what's going to happen with the rest of the building and your loads? Basically, your demolition happens. It's like construction in reverse. So it's dangerous, but it's also expensive to have people in there pulling various items out. But for some of your better stuff, it is worth people going in there. And then the more people that use recycled materials in building, the more value there is going to be in people using recycled materials and buildings being deconstructed in a fashion that enables that recycling rather than just smashing it all up and taking it to landfill, which happens. That's a lot of landfill. But the problem with recycled materials, particularly recycled timber, is nails and things like that. And things are not straight as well. I built a shed recently from recycled timber. I probably wouldn't do it again, to be flat out honest. It just requires so much time, and things don't end up being perfectly straight. Like you get things as straight as you possibly can, but things don't end up perfectly straight. Which it's all right, but then when it comes to flashings and things like that, it's difficult. So I completely understand, and I'm much the same. I think okay, I'd probably use just new pine, and then go through that process. The whole build would be much quicker.
It's better off turning recycled timber and trying to clear out all the nails and everything than just turning it into mulch.
Yeah.
Just turn it into chippings or mulch or something like that. Just recycle it that way instead of trying to use it to build anything. Because it's already warped. It's already been through the whole process of being cut and everything, and it's sat there for however many years.
Yeah.
So what damage, you don't really know what's happened to it.
Oh, if you know your timber, you can work. Yeah, and that's the other issue with using recycled timber is, to follow the letter of the law, you have to have someone stress grade it, or to say, yes, that old piece of jarrah, yes, that is going to be F27 because it doesn't have any gum veins and whatever in it. You've got to have people cast their eye over it and certify it if you follow the letter of the law. Because there are defects and things. Now all those defects, when a piece of timber has been cut down and milled and dried, and then you buy it from the timber supplier, it's already gone through somebody checking that piece of timber over and going, has that stress grading. You've got that. Yeah, you've got that. When you're buying timber that's from an old building that you've pulled out, you've got no idea of the provenance or the stress grading of that, and that comes down to you to make that decision, or you get someone else to stress grade it. I wouldn't go. I don't agree with you entirely that it should be mulch. Like with that shed that I built, yeah, okay, maybe the shed component is far more time consuming using old timber, but the results I got from the carport coming off of that are just beautiful. Like really old jarrah, planed and sanded back. It just looks lovely, and you get a real strength from your cross section of timber that you just can't get from your pine. You've got to use much bulkier elements, that sort of thing. But in the main, it's when it comes to time and money, it's typically not in your client's best interest. So there's definitely significant impediments and real hurdles to using recycled materials. But there are opportunities there as well. And also, the best way of recycling building materials is to reuse or repurpose a building. Rather than knocking it down, what can you actually do with it? Yeah, so looking at the lifespan of materials, extending building lifespan. So that's about building. Well, it's partly about building detail and things. I spoke about that platform floor with chipboard gets wet. So the best scenario is if it never gets wet to begin with. If you've got really good building details and flashing details and so on to ensure a house keeps itself in good condition, well, that house will live on and hopefully be used for a far longer period of time, extending the building lifespan. Also, if you think about things like aging in place, like how somebody can live in that house today, have a family, have have a retirement, etc., have an old age all in that one house. That has its social benefits, but it also has its environmental benefits because we're doing less of this knocking down and rebuilding as a result of that. Yeah, encourage development of improved low impact materials. Yeah, so think about what goes into the production of these. We spoke about embodied energy, but it's not just embodied energy. There are a lot of chemical processes and like side effects of manufacture of materials as well. Yeah, and that even goes down to mining. Yeah, minimise energy use for transportation of materials. So sourcing stuff locally. Typically, a big influence on that is going to be cost anyhow. Chemical emissions as well. So I spoke about that. So common composition of a building site's construction waste. So by and large, soil's the main thing, but if soil can be used appropriately elsewhere, it's got to save you a lot in soil dumping. If you can find somebody who's close by who wants that soil, that's good. Concrete-based masonry, brick and tiles, timber. So these have a very high embodied energy. Timber, less so. Yeah, we'll flick through this fairly quickly because I do want to touch on the project as well before we hit the break. This is a fairly good table. So when we talk about the energy inputs that are required for building materials, embodied energy, like megajoules per square meter. And per square meter is probably the better form of comparison for us rather than cubic meter, because something like, you'd say, fibre cement sheet has a really high embodied energy per cubic meter, but we don't use it in cubic meters. We use it as a thin, like a 9mm sheet or a 6mm sheet. So by square meter is probably a very good comparison. And then when you look at that, so our what tops it out is cavity clay brick wall with plasterboard internal lining and acrylic paint finish. Highest embodied energy. So that's that cavity brick wall I showed earlier on. That's 2 leagues of brickwork. And then right down the bottom of that, timber frame, fibre cement, weatherboard wall. 169 megajoules per square meter. But also, just separating out the cost of labour and everything from this, what's going to be our cheapest option, just dollar terms for the materials for fibre cement sheet on timber frame or cavity masonry? Anybody got a guess? Timber frame. And that is the case so often because electricity is expensive, energy costs a lot. Typically, your cheaper options are going to be your most environmentally friendly in terms of embodied energy. Anyhow, it's a pretty good guide to that. More tables comparing embodied energy of various materials. that's another thing to think about is the process in timber. So I said timber has a very low embodied energy, but it is it is kiln dried as well. To turn it around from logs to timber which we can use quickly, it's got to be, it does get baked. Whereas whereas your hardwoods are typically or less often kiln dried, because if you take the moisture out of a hardwood really rapidly, it cracks, because there's just basically it relies on the cell structure of that timber. Softwood cell structure is different than hardwood cell structure. When you dry out hardwoods too quickly, they crack. But that's also why hardwoods are really expensive, because they have to be seasoned really slowly. So there's a very long lead time from when it's cut from the tree to the time that you buy it as a piece of hardwood. Yeah, what are the high ones in that? So we've got aluminium. Aluminium tops it out by a lot, and then rubber and PVC. So yeah, a lot of embodied energy in aluminium. Okay, comparison of embodied energy of various different building materials. Fairly much covered that as well. Yeah. Which buildings can be recycled? One, yeah, maybe. Oh, let me know if you think it's naff or not. But there was a statement I heard it expressed once. There's no such thing as waste, only stuff in the wrong place. In the everything, all these bits and pieces of material can be used, and are valuable for something. Even soil is valuable for something in the right place. And so probably and a good way of thinking about the proper use of things and recycling is to think, okay, where can that piece be used, and where is its value gonna lie? And so you've got to think about what products can be recycled. So steel, super easy to recycle, and yeah, and lots of spare steel on a site. Well, yeah, you get money for it. You do need it, like when you're talking about sheet steel and stuff like that. You need a pretty decent trailer load to make it worth your while. But if you're going to be paying $80 a trailer or something for dumping stuff, as opposed to getting $100 for that trailer load, definitely well worth it if your only other option is dumping it. And aluminium, get a lot of money for aluminium. Gypsum plasterboard. So there's plasterboard that you can buy that has recycled content. So recycled plasterboard. But I don't know about how, what the avenues for taking back the offcuts of plasterboard are. Typically that's not done. Timber, recycled. Concrete can be crushed up for road base. Glass, easily recycled. Carpet, I didn't know about. I don't know about the process for recycling carpet. Bricks and tiles, once again, crushed up for road base and for rubble. And hard plastics can be recycled. Oh, that's another thing, didn't really cover, but of course it's fairly possibly the elephant in the room. Is about reduction. It's about the size of buildings as well. So yeah, obviously in a small house, you're going to use a lot less building materials and have a lot less environmental impact than you are with a big house. If you have a big house, far more impact, far more cost. Obviously, that's probably something that you may be able to discuss with your client, but it very much comes down to your client's desires there. Old red bricks, fantastic for reuse for paving. And has everybody seen building projects using old? Actually, possibly, yeah.
Yeah, my sister, she had two buildings. It was like a garage and a laundry.
Yeah.
They've knocked down the garage and they've used some of the bricks as just parking because it can't be used for anything structural because the degradation or the strength of it is not as strong as it was.
Yeah, yeah. So, well, in some situations they can't be reused. Typically bricks aren't used in a structural sense anyhow, unless we're doing cavity brick. Typically, it's going to be an external skin. But yeah, but some bricks can be reused for the actual building of walls as well. And you see it about the place. It's a place I drive past on Glen Osmond Road a lot, sort of near. It's got to be. I think it's Kensington Road. Where Kensington Road hits Glen Osmond there. There's a fairly interesting design house that's obviously used recycled bricks because some of them are grey, some of them got bits of paint on them, some of them bit of grey paint, some a bit of white paint, some and it's a bit of a thing at the moment. I think not sure I'm not sure if that's going to happen with these buildings down that are being built down here. On that corner just coming from South Road as well, they might be using recycled bricks elements. Yeah, but it's something you see more and more. It's a bit of a design trend at the moment. But yeah, definitely for paving. Yeah, concrete being recycled for as road base, but not only as road base, but as base for buildings as well. Because under buildings, what you want is a very stable foundation, and this compacted rubble that has concrete in it can be compacted very hard. Recycling windows, kind of difficult, but if you're doing renovations and things you want to match old windows, it's a very good option. We'll just touch on this briefly. Doesn't relate too much to this subject, but indoor air quality is an incredibly important thing, and some clients may have desires around that. But the most important thing is about condensation in buildings and about mold growth. So you want to ensure that that you don't properly insulating a building means that you don't get as much condensation in that building, because if you've got warm air with a gas heater is probably the worst, where you've got a lot of moisture in the air, and then you've got cold walls or cold windows. It forms condensation wherever it's cold, and that condensation forms inside the house, and that can be a source of mold. Mold's really not very healthy. But then also in terms of other things around the building elements, such as the off gassing from various different materials and things like that can be an important consideration. And use of natural materials can be very, very important to people with high sensitivity to things. Yeah. And that's not too relevant to us, but using things like straw bales and hempcrete and rammed earth, compressed blocks, mud bricks, cob. Actually, close the current tab. Right, so that's a lot of the sort of more environmental considerations in a nutshell. So to prepare you for your meeting with the client, it's probably good to have a brush up on that. But particularly, it's about orientation. So the stuff we covered first about the orientation building in terms of sun and cross flow ventilation, but then also about materials and choices, etc. Actually, or this is going into the client consultation with that. That's going to happen next week. I will be introducing that to you today. but possibly, yeah. What I think is probably most pressing is that we have a look at the building and the building project first before I discuss any of this. So we've looked at it insofar as we've had a look at our client brief already. Last week we touched on that. So maximise views, passive design principles. I'd like to remove the front fence and extend the deck from the mills area to 3 metres by 3 metres. So we're doing some work. We're meeting some objectives. But the practical side of what we've actually got to do is produce a set of drawings. So we have to produce that set of drawings suitable to go to planning approval. Some of that information comes directly from City of Mitcham to say these are the drawings we need for planning approval. But then also we've got some stipulations in the unit of competency, the things that we have to assess for that say, well, students also have to be able to do this and this and this, right? They don't directly come from Mitcham. Sometimes those things come from other projects or other council areas. So a couple of things on top of that, beware, but they're all outlined in here as to what you have to do. So we've got to produce that set of drawings plus some supporting documents. So our supporting documents will be bushfire attack level analysis. So we've got to provide information about that. We've got to and provide some of the reports as well. So you're given some reports, and just a heads up, you can't trust everything in terms of the reports that you're given. That's part of it, and that's also what you'll find in a workplace situation as well. Things go into the wrong place sometimes. You might get a soil report, or like, God forbid if it ever happens, it's not a great thing, but you may get a soil report or a footing report which is incorrect for the building, or we get some information which is like, that's not the right thing for this, or there's something in that that's wrong. Through the process of this, you're also required to find those inconsistencies as well with some of this information that you're supplied. I'll let you know. But put simply, what we're going to be working towards later today. Is there anybody who can't make it? Richard, yes, you can't make it this evening. I'll try to keep you up to speed as much as possible. Andreas will record it, and you're fairly handy on Revit anyhow. Yeah, well then, yeah. So you'll be fine. You'll be fine. But yeah. So what was I going to say? Yeah. So what we'll be going through with Andreas is the actual Revit component about mucking around with that site and that building, turning things around and producing those surfaces in order to get all this information ready to go to the council. So that's what you guys are doing, and that's what you do as a job as drafters, is predominantly getting stuff ready to go to council for assessment. Sometimes you're drawing stuff for clients, but predominantly the bread and butter is getting stuff ready for council. So develop models to meet your requirements of. So when it says models, we're talking about drawings. So you've got to get that information packaged to meet the requirements of your site analysis, contours, materials, noise control. So we've got a busy road. Energy efficiency. So we know a fair bit about energy efficiency now. Fire, to meet the medium bushfire attack levels, and we'll go into that further. We can't cover everything today. That's something that comes a little bit more in the tail end of the project. And to meet development plan. So you've had a look at your development plan, got a bit of understanding about energy efficiency. Develop sheets to meet requirements of planning approval. So you'll have a cover sheet that will show a 3D view of the premises. That's probably going to be the last thing you do, because you're going to be doing all this stuff first, and then the last thing you put together is your image to go on the front. Client's name, contact details. That's fairly simple, and that can be fictitious if you wish. Either way, project title, site address, well you've got that, this is all information given to you. Student details and sheet schedule. We want to see on that cover sheet your schedule of all your other sheets. So once again, probably one of the later things you've got to be doing, pulling this together, because you've got to decide, okay, well I want this sheet in this order, etc. And order does matter. Just a really, and I'll go into plans and sheeting and so on later, but just as a real general rule, we start big, we think about the neighbourhood and the environment, then we get to the site, then we get to the building, then we get to the details. Just in a nutshell, that's the way sheets are laid out. You start from big picture and go to small picture. So your site analysis plan, neighbouring structures, services, vegetation, fence, and shadows. Include all of that information on your site analysis plan. Site plan has to be dimensioned. Definitely needs a north indicator. So site, that's an essential thing for the site plan. Has contours, has dimensioned site setbacks. Access and egress from the road and around site. So what are we doing? What are we doing with vehicles? How are they coming in and going out? You want actually. Well, I'll go through this fairly quickly because because many of us are heading off down to the BDA thing in about 8 minutes or so. So I'll just be very quick. So you want a floor plan. It's going to have dimensions. It's going to show all of your openings, wall thicknesses, door clearances. You're going to have indicators to show which door and window is which and what type of wall construction it is. You're going to have standardised size windows in there. So I spoke about size of plasterboard sheets, size of bricks. We've also got standard window sizes. A very good reason for that is because they fit in with bricks. So yeah, so that's something you're going to have to check. You're going to have to make sure. Does anybody know where you get standard door and window sizes from?
Is it a stick bar?
So from your window manufacturer, Stegbar probably produced the easiest to read table, but yeah, just about any window manufacturer, they're going to have their table of standardised doors and windows. Yeah, Stegbar's the easiest one to read, and I'd go with that. And that's why we use it, hand it out a lot. Yeah, elevations, so show elevations of the building, and then 2 sections. So so you'll have some details there of roof structure, wall structure, floor structure, and internal materials. That's something that we can go through a lot more into the future. I'm just sort of giving you the heads up today before Andreas is here later on. So you'll be looking at doing a 3D view, looking at doing a sustainability sheet. So that's information to your client. There's also information to council about how you're meeting these criteria. Your door and window schedule, and then some reports. So solar panel report, fire safety report, and then any additional requirements set out by council. And then you do the submission for council approval. So that's the crux of what we're actually doing in this subject, is producing that drawing set and those reports to go off to council. And what we'll be looking at today is that mucking around with that site plan, mucking around with the building on the site, creating that surface, etc. So any questions in regards to that for later? All good? Okay, fantastic. Well, I'll just go, actually, no, I think, yeah, no, what I will do, I will go through the what you have to do for client consult, give you a bit of tips. Take it away, think about it, prepare for that over the next couple of days. Because we've got client consult and building designer consult on Wednesday. I'll just record a small section for you. I think it's the best if you like. But mainly it's about you. Yeah. Look, I'll actually no. I'll just do that for everybody. We've got Andreas for our next session here. Tomorrow during the day, I'll have a bit of time to sit down in front of the computer, just record a quick thing, a 5-minute video saying, how do you go about preparing for a consult? Get that out to you. You guys can watch that tomorrow. So look out for that. I'll email everybody so we're all on the same footing with that. All right, fantastic. Well, I'll conclude it there.